Hello, this is the final design project for BME 214 lab. My name is Malik Carter.
I'm Kayla Fisher.
I'm Ryan Pine.
And I'm Nikki Puttapetti.
Our clinical problem revolves around Achilles tendon surgery. So the Achilles tendon is in the lower leg and it's very prone to degeneration and also rupturing when exposed to large tensile loads. The individuals affected are mostly athletes and elders, but there's an added factor when it comes to athletes as it inhibits their ability to play. About 8 to 18 per 100,000 people annually in the United States are affected, but among athletes specifically, 6,000 to 18,000 per 100,000 athletes annually in the U.S. are affected by Achilles tendon injuries. So currently, the main way to fix it is surgery. So surgery to repair tendon risks severe damage to nerves. Paresthesia risk is about 1.7% to 23%, and then also swelling and scar tissue can form around the nerves, trapping it, causing pain or tingling sensations in the patients. And then for blood vessels lay very closely to the Achilles tendon during surgery, which means that there could be severe damage to those blood vessels. Also, during recovery, reduced calf movement can cause blood to pool, which could create a large risk for deep vein thrombosis. Current therapeutic strategies and standards to reduce DVT that hold right now are using splits or boots during recovery, elevating and icing the foot, and also physical therapy. Our problem statement is, due to the fact that tendons are supplied with a rich capillary network, replacing them via surgery without causing damage to that network is very difficult. This often leads to damage to the blood vessels and nerves surrounding the newly replaced tendon for athletes and blue-collar workers who are the most common patients for this surgery. This leads to patient dissatisfaction, post-operation pains, and costly follow-up procedures. And our need statement is, there's a pressing need for a method of preventing or decreasing the occurrence of these damages to the blood vessels and nerves surrounding a tendon that has been replaced in athletes and blue-collar workers in order to reduce post-op pain, expensive follow-up procedures, and improve pain satisfaction. And then the objective of our study is to temporarily stop blood flow through these large vessels surrounding the Achilles tendon, which will make the vessels smaller during surgery and therefore easier to get out of the way in order to reach the tendon to perform the surgery, and it is less likely to cause damage.
The image on the right of the slide shows the schematic of our arterial tourniquet clip in our CAD drawing. It shows that the specifications are about 140 centimeters by 10 centimeters by 25 centimeters, and this can change, but this is what fit best with our CAD. And it is a single high tension hinge, and then it uses ABS plastic, which as we will discuss later, PEEK was the better material to use, but that wasn't available to us, so we used ABS. Some performance requirements for our clip is that it needs to withstand the force of the blood vessel so that it doesn't break, and then it also needs to be easy to work with because we don't want this to be something that causes an issue for the surgeons while they are doing surgery. And then a competitive advantage that we have is that this is more of a localized targeting of the blood vessel rather than using a tourniquet that cuts blood flow for the whole limb. So this makes it better, and you therefore don't have to lose a whole limb and you just lose one blood vessel.
For our materials and methods, we designed 3 different testing protocols. The first one being the occlusion testing, which uses the Instron device to determine the minimum occlusion force for 99% occlusion of the peroneal artery. We want to know how much force we need to occlude that artery so we can use that data to develop the device better. Some of the variables for that protocol, the independent ones being vessel size, pad hardness, and surface state, and the dependent ones being percent flow reduction, closing force, peak jaw pressure, and pressure uniformity. The next protocol we have is the FEA testing protocol, or finite element analysis, where a force of 300 newtons was applied to the handles, as that is the location that will experience the greatest amount of force during use. And the independent variables for that were the element mesh, and the dependent variables were the safety factor. The final protocol we designed was the compression testing protocol, where specimens ABS specimens were aligned and compressed using the Instron until the force experienced a 20% drop in newtons. So we replicated that 5 different times for 5 different specimens, and as you can see, the independent variables were the specimen material, which was ABS, and the dependent variables were force and displacement.
Upon testing our material, which was ABS, through both FEA testing as well as mechanical property testing in the lab, we determined that our device meets the safety requirements that we implemented to ensure functionality during use in surgery. These requirements basically included being able to withstand the amount of grip load that we applied, which was found through researching the highest recorded grip strengths, as well as being able to apply proper pressure to blood vessels and tissues without breaking or damaging said blood vessels and tissues. The device, even under an applied load at the handle portion, was able to withstand the load that we researched and remain above the target safety factor, as well as remain under the researched load that would inflict damage upon human tissue. It can be seen that our device is entirely blue in the FEA diagram, which indicates that it is above the target safety factor, which then ensures that the device is safe to use and functional. To conclude and summarize some of our results, we researched and determined that our material could withstand the maximum amount of grip load that could be applied to our device, which can also be seen through the large force values in the results table in the previous slide. We also determined that our device would not deform during surgery, as the average diameter displacement during our material testing was minimal at a value of 0.48 millimeters. This can indicate that there's no risk of damaging blood vessels and tissues further during the use of our device. Through FEA analysis, we also determined that our device, with the material that we chose to make it out of, would remain above the target safety factor, which ensures safety and functionality during use in the operating room. Finally, we determined that our device would not cause damage to tissues and blood vessels, as stated previously, and that can be seen in the results table through the minimal amount of displacement and the fact that the device remains above the target safety factor. One shortcoming that we came across during our modeling and testing of our device is that we did not have access to the proper materials that we determined would be the most optimal and ideal to make our device out of, which is PEEK, or PEEK. So instead of using that material, we chose a more accessible material in the form of ABS.
Some future work that could be used to make our device better would be adding grips onto the handles to make it more user-friendly, as this would make it easier to use in the real life. We also could make it a more functional structure, making it easier to use within the body and smaller to fit into certain places. And then also making it more universal, because we made it to be used for the Achilles part, but we could use this in other parts of the body during surgery on other blood vessels. And then we also could make it more universal for a variety of patients. And also in the future, since we determined that PEEK would have been the most ideal 3D printing material, we could use this as our material to print, which would make it work best with our design. We want to thank the TAs as well as Vlad for the assistance and support throughout this lab project.
Thank you.